Welcome to the office for one last video on subgroups and cyclic subgroups and really cyclic groups. So let's take a look at our notes here. A couple of definitions, followed by an example. Let G be a group and let A be some element of that group. Then the subgroup, H in our previous theorem here, then that subgroup of G is called the cyclic group of G generated by the element A. And it's denoted by this. So what you want to keep in mind is right, the equality of these two things. A itself is the set of elements A to the n, where n belongs to the the integers here. So this does include A to the 0, and it includes A to the -5th, right? It has these inverses and these and the identity there embedded within it. Excellent. So that is a subgroup, right? A is a subgroup of G, where A is some element of G. So an element A of a group G generates G if it is the case that the subset generated by A is the entire group. So a group is cyclic if there is such an element A that does indeed generate all of G. Pretty straightforward there. All right. So if we wanted to consider really just as some basic examples, if I wanted to consider, let's see here, in in Z under addition, right? Because that is the group under or for the set Z. We have inverses, we have identity, that sort of thing. Multiplication is not, integers are not a group under multiplication because we don't have inverses, that sort of a thing there. So in this particular group, if we consider what's generated by the number 3, here we've been using multiplication notation, so multiplicative notation there. This is going to be written in addition notation. This is going to be 3n, where n is an integer, and that should look pretty familiar to us as the set that we were talking about before. That's just 3z. So this is a subgroup of the integers under addition. Excellent. In Z4, which we already talked about earlier as well, we could look at 2, for example. If I want to talk about the subset generated by 2, I can talk about all of the powers of 2. Okay, this is, let's see here, 2 to the first power, of course, includes 2. 2 to the second power, 2 times 2 is 4, but this is Z4, so it's addition, not multiplication. So 2, so 1 times 2 is 2. 2 is 2 plus 2, so 2 times 2. That's why I was thinking there is 4. 4 mod 4 is 0, and then of course any higher power is just going to alternate between 2 and 0. So that's exactly it. That's that subset that we were talking about earlier. Let's see here. Let's kind of separate these examples. I don't want us to confuse those. In Z4 still, if I wanted to talk about the set generated by 3, I could talk about, right, 3, 1, 3. That's just that. 2 3s. 3 plus 3 is 6. 6 mod 4 is 2. And then, of course, I can talk about 3 times 3, so 3 plus 3 plus 3. That's 9, which is 1 mod 4. And then 4 3s, 3 plus 3 plus 3 plus 3. I think that was 4 of them. That's 12, and 12 mod 4 is 0. So we end up with the entire set. So it works out to be that 3 generates Z4. Excellent. We can also show that 1 generates all of Z4 as well. And of course, 0 is just the trivial subgroup, right? 0 generates this trivial subgroup. And So let's see here. Oh, you know what? We could have given another example here in Z. We could certainly give that 1 and -1 both generate all of Z, because we're talking about multiples there. Okay, so if I wanted to take a look in, let's see here, U7, for example. Actually, you know what? Let's go with, well, yeah, sure. Let's start with U7, right? The complex numbers of unit length, the seventh roots of unity here. If I were to look at any of these, this entire thing is generated by any any of its elements except for the identity. So this is equal to A, right? It can be generated by any element where A is not equal to 1. So that's really cool. Um, if I wanted to, we could take a look at, for example, U6. This one is a little bit more interesting. So the units, sorry, the roots of unity, sixth roots of unity. If I consider, let's see here, that would be, um, if I write these all out explicitly, I would have 1, which is equal to e to the 0 I. I could have e to the pi over, let's see here, pi over 3I is what I want. E to the 2 pi over 3I. I could have e to the 4 pi over 3I. I have e to the 6 pi. Let's see here. 1, 2. Oh, I skipped one. I'm sorry here. I'd like these to be in order. 3 pi over 3 is just pi I. E to the 4 pi over 3I. E to the 5 pi over 3I. And then, of course, e to the 6 pi over 3 is just 2 pi I, which is 0 pi. Or 0I. Yeah. So that's our 1, 2, 3, 4, 5, 6 sixth roots of unity. If I were to consider what's generated by 1, well, that's just the trivial subset, right? That's the identity under multiplication, because we're working in multiplication here. If I wanted to talk about what's generated by e to the pi over 3, I, well, I want to recognize that since we're working in multiplication notation, that's just raising it to a power, and that generates the entire set, your roots of sixth roots of unity, right? Raise it to a power, and I'm going to get each one of these things. Now, if I were to talk about e to the 2 pi over 3I, that looks a little bit different. Okay, I of course get e to the 2 pi over 3I, but then when I multiply it by itself, right, two of these, this times itself, that's going to give me e to the 4 pi over 3I. And then when I multiply it by that again, it's going to give me 6 pi over 3, yeah, which is just e to the 0I. And then when I multiply by itself again, it brings me back to here. So this is a subset of just 3 elements. And then I can also look at e to the pi over 2I. Let's see here. I'm sorry, pi I, not pi over 2. Pi I, there we go. And this is actually just going to be um, e to the pi I, and then multiply it by itself, right? Raise it to the second power, and I'm going to get e to the 2 pi, so e to the 0 I there, and that's it. So I have the trivial subset. I have a generating element for the entire thing. So this is a cyclic group. I have the cyclic subgroup of 3 elements. I have the cyclic subgroup of 2 elements. So this is pretty cool. What you'll notice that there are no subgroups. There are no non-trivial subgroups of this. No non-trivial subgroups. I would encourage you to take a brief look, right? You would split it up in the same way we did here, 2 pi divided by 7 instead of 2 pi divided by 6. So 1 e to the 2 pi divided by 7, and then take the powers to get you our roots of unity. And then notice that for each one of those 7 things, it either generates the trivial subset or it generates the entire set itself. So this is cyclic and this is cyclic. This one here, our 6th roots of unity, has a couple different subgroups, whereas the 7th roots of unity do not. So that's kind of cool to consider and take a look at, something to play with. But that's all that we really need to take a look at. So here's a variety of examples of sets that are cyclic. There are, of course, groups that are not cyclic. I suppose maybe we should comment on that. For example, the Klein 4 group is not a cyclic group because there's not one element that's going to generate the whole thing, right? A generates this subgroup, B generates this subgroup, C generates this subgroup, and E generates just that subgroup. Nothing generates the entire. So these are all cyclic subgroups, but the group itself is not cyclic. All right, yeah, that should be pretty good for now. Thank you for your time and attention. That is the end of section 5. Yay! Have yourself a great day. I'll see you guys back in the classroom soon.